Welcome everyone. Today, we'll explore the mechanical properties of materials, key factors like strength, elasticity, and durability that influence how materials perform under different conditions. Understanding these properties is essential for safe and efficient engineering design. Mechanical properties define how materials respond to forces and environmental conditions. We'll start by reviewing the fundamentals and loading conditions, which set the stage for understanding material behavior in real-world applications. Mechanical properties describe how materials respond to applied forces and environmental conditions. These properties include elasticity, plasticity, strength, ductility, and hardness, which collectively determine a material's suitability for specific applications. Elasticity refers to the ability of a material to return to its original shape after deformation, while plasticity indicates permanent deformation under stress. Strength measures the maximum stress a material can withstand without failure, and ductility reflects its ability to deform plastically before fracture. Hardness, on the other hand, is the resistance to localized plastic deformation, often assessed through indentation tests. These properties are influenced by factors such as microstructure, temperature, strain rate, and environmental conditions like corrosion or humidity. Understanding these characteristics is essential for engineers to design components that meet safety, durability, and performance requirements. For example, high-strength steels are chosen for structural applications, while ductile metals are preferred where energy absorption is critical. Mechanical properties also guide inspection intervals and maintenance strategies, ensuring that components remain fit for service throughout their life cycle. By analyzing stress-strain behavior, engineers can predict failure modes and optimize material selection for different loading conditions, thereby enhancing reliability and reducing operational risks. Loading refers to the application of forces or stresses on a material, which can occur in various forms such as tension, compression, shear, torsion, and bending. Each loading mode induces different stress states and deformation patterns. Tensile loading stretches the material, while compression shortens it. Shear loading causes layers within the material to slide relative to each other, and torsion applies a twisting force. Bending combines tension and compression across a section. Loading can be static, where forces remain constant over time, or dynamic, involving fluctuating or impact forces. Multi-axial loading occurs when multiple stress components act simultaneously, complicating analysis and design. Understanding loading conditions is crucial because materials exhibit different strengths and failure mechanisms under varying loads. For instance, brittle materials may fail suddenly under tension but withstand compression better, whereas ductile metals can absorb significant energy before fracturing. Engineers must consider service conditions, including temperature variations and environmental factors, which can alter material behavior under load. Proper assessment of loading scenarios ensures accurate stress calculations, prevents unexpected failures, and supports the development of safe and efficient structures. Next, we'll look at stress and strain fundamentals and tensile properties, which are critical for predicting material performance under load. Stress and strain are fundamental concepts in mechanics that describe how materials respond to external forces. Stress is defined as force per unit area and can be categorized into normal stress with equation is sigma equals F over A and shear stress with equation is tau equals V over A. Normal stress acts perpendicular to a surface, while shear stress acts parallel. Strain measures deformation relative to the original dimensions, expressed as normal strain with equation is epsilon equals delta L over L or shear strain with equation is gamma equals delta X over H. In the elastic region, stress and strain are proportional, following Hooke's law with equation is sigma equals E times epsilon, where E is Young's modulus, a measure of stiffness. Beyond the elastic limit, materials enter the plastic region, where permanent deformation occurs. Understanding these relationships is critical for predicting material behavior under load and designing components that avoid failure. Engineers use stress-strain curves to identify key properties such as yield strength, ultimate tensile strength, and ductility. These curves also reveal how materials transition from elastic to plastic behavior, providing insights into energy absorption and toughness. Accurate stress and strain analysis ensures structural integrity and informs material selection for diverse engineering applications. Tensile properties describe how materials behave under stretching forces and are essential for evaluating structural performance. Key parameters include yield strength or sigma sub y, which marks the onset of plastic deformation, and ultimate tensile strength or UTS, the maximum stress a material can withstand before necking. Ductility is assessed through elongation and reduction of area, indicating the material's ability to deform plastically before fracture. The modulus of elasticity or E is derived from the slope of the elastic region in the stress-strain curve, reflecting stiffness. Strain hardening occurs between yield and UTS, where the material becomes stronger as it deforms. These properties are determined through tensile testing, where a specimen is pulled until failure while measuring load and elongation. Understanding tensile behavior helps engineers design components that resist failure under operational loads. For example, high UTS materials are chosen for load-bearing applications, while ductile materials are preferred where energy absorption is critical. Tensile properties also influence manufacturing processes, such as forming and welding, and play a vital role in safety assessments and material certification. Beyond tensile behavior, we also consider compression, bearing, shear properties, and hardness, each important for different applications. Compression properties measure a material's ability to resist shortening under axial loads. Ductile metals typically exhibit plastic flow without necking, while brittle materials may fail suddenly. Bearing properties relate to localized contact stresses, such as those under bolts or pins, and depend on factors like plate thickness and hole diameter. Shear properties describe resistance to sliding along planes within the material, commonly encountered in fasteners and torsional components. Shear stress is calculated as tau equals V over A, where V equals shear force, the force acting parallel to the surface, A equals area, the cross-sectional area over which the shear force acts. And shear modulus or G defines elastic behavior under shear loads. These properties are critical for designing joints, supports, and connections that experience complex loading. Failure modes vary: buckling in slender columns under compression, ovalization in bearing surfaces, and shear fracture in bolts. Engineers must account for these behaviors to ensure structural integrity, especially in assemblies subjected to dynamic or multiaxial stresses. Proper understanding of compression, bearing, and shear properties enables accurate load distribution, minimizes stress concentrations, and enhances the reliability of mechanical systems. Hardness is the resistance of a material to localized plastic deformation, typically measured through indentation tests. Common scales include Brinell or HBW, Vickers or HV, and Rockwell or HRC or HRB, each using different indenter shapes and loads. Hardness correlates approximately with tensile strength for steels, making it a useful indicator of material performance. It is influenced by microstructure, heat treatment, and surface condition. Hardness testing is widely used for quality control, where resistance evaluation, and detecting gradients in case-hardened or welded components. Portable hardness testers allow field measurements, supporting maintenance and inspection activities. Understanding hardness helps engineers select materials for applications involving abrasion or contact stresses and verify that components meet specified requirements. It also aids in predicting service life and identifying areas susceptible to wear or failure. Now, let's discuss properties that change over time, like creep and stress rupture, and toughness, which measures energy absorption before fracture. Creep is the time-dependent deformation of materials under constant stress and temperature, critical in high-temperature applications like turbines and boilers. It occurs in three stages: primary, decelerating rate; secondary, steady rate; and tertiary, accelerating rate leading to rupture. Stress rupture refers to the time to fracture under constant stress and temperature, often represented on log time plots. These properties are influenced by temperature, stress level, and microstructural stability. Engineers use parameters like Larson-Miller to predict long-term performance and schedule inspections. Understanding creep and stress rupture is essential for preventing catastrophic failures in components exposed to prolonged high-temperature service. Proper material selection and design adjustments, such as reducing operating stress or improving cooling, mitigate creep damage and extend component life. Toughness measures a material's ability to absorb energy before fracture, represented by the area under the stress-strain curve. High toughness indicates better damage tolerance and resistance to crack propagation. Impact toughness, assessed through sharp EV-notch tests, evaluates energy absorption under high strain rates. Many steels exhibit a ductile to brittle transition temperature or DBTT, below which fracture occurs with minimal plastic deformation. Notch toughness reflects sensitivity to stress concentrators, where sharp notches significantly reduce apparent strength. Fracture toughness or K_IC quantifies resistance to crack growth under plane strain conditions and is vital for damage-tolerant design. These properties are influenced by temperature, strain rate, and microstructure. Engineers rely on toughness data to ensure safety in structures subjected to dynamic loads, impacts, or flaw presence. Proper design, material selection, and inspection strategies minimize brittle failures and enhance structural reliability. Finally, we'll cover fatigue and crack growth, key factors in long-term reliability. Fatigue is the progressive damage caused by cyclic loading, often at stress levels below the material's yield strength. It accounts for a significant proportion of service failures in mechanical systems. Fatigue life is represented by SN curves, Wöhler curves, which plot stress amplitude against cycles to failure on a log-log scale. Some materials, like steels, exhibit an endurance limit, below which fatigue failure is unlikely, while non-ferrous metals generally do not. Factors such as mean stress, surface finish, size, and environmental conditions influence fatigue performance. Engineers apply correction factors and safety margins to account for variability and ensure reliability. Understanding fatigue behavior is essential for designing components subjected to repeated loading, such as shafts, gears, and structural members, and for planning maintenance intervals to prevent unexpected failures. Fatigue crack growth describes how existing cracks propagate under cyclic loading. Paris law models this behavior as dA/dN equals C times open parenthesis delta K close parenthesis to the power m, where dA/dN is the crack growth rate per cycle, delta K is the stress intensity range, and C and m are material constants. Crack growth occurs in three regions: near threshold, slow growth, Paris region, stable growth, and rapid growth approaching fracture toughness or K_IC. Engineers integrate crack growth rates to predict remaining life and schedule inspections before critical crack size is reached. Factors such as load spectrum, environment, and residual stresses affect growth rates. Understanding fatigue crack propagation is crucial for damage-tolerant design and maintenance planning, ensuring structural integrity and preventing catastrophic failures in components like aircraft structures, pressure vessels, and rotating machinery.